Today, I want to head towards the end of this chapter by talking about arc length and curvature. For the moment, it'll be most convenient for me to continue thinking of the t as being time and r as being position. I want to think of the graph of a vector-valued function starting at t equals a and traveling along the curve until I get to t equal b. What I'd like to do is, I'd like to figure out how much distance along the curve I've traveled, the arc length. We will pursue the same idea that we did back in the second semester. I'm going to take the range of t values from t equal a to t equal b and divide it up into a great number of smaller subintervals. On each one of these smaller subintervals of t numbers, I'm going to make the subdivisions so small that the speed can be more or less thought of as a constant. The distance that an object travels is its speed multiplied by the amount of time used. So I'll take the length of r prime, evaluate it at some t value within subinterval number I, multiply it by the amount of time that corresponds to that subinterval, and this will approximately be the amount of arc length that goes with one of these pieces. As we did in the second semester, we'll add up all those pieces, then take the limit as all of the delta t's tend to 0. You should recall that this is the definition of a definite integral. I'll use a lowercase cursive s for arc length, and assuming that all of these derivatives and integrals can be done, the arc length is just the integral from the beginning t value to the ending t value of the speed with respect to time. In most cases, the integral is too complicated to work out in closed form, even though if the speed is continuous, then the integral certainly exists. As an example, I'm going to look at the vector-valued function whose graph is a helix. I want to start at t equal 1, end at t equal 2, and calculate the arc length along this graph. Calculating the derivative, then its magnitude to get the speed, when you square negative 5 sine of t, you get 25 sine squared t. Here I'll have 25 cosine squared t, and 2 squared is 4. Combining the first two terms in the usual way, I get 25, and then I must add 4. In this particular case, for this particular vector-valued function, the speed works out to be a constant, which means that it'll be easy to figure out what the arc length is. The length along the helix, starting at t equal 1, ending at t equal 2, is radical 29 units of distance. There's more than one way to describe where you're at on a curve, though. I could just have r of t as usual and do all of the usual things, or I could do this instead. I could imagine picking some particular point on my curve with a corresponding t value, t equals a, and then for t values that are bigger than a, as I travel out along my curve, what I could do is I could figure out how much arc length has been consumed. To get the s value that corresponds to a given t value, I'll have to integrate starting at t value a, ending at whatever particular t value that I'm interested in. I must integrate the speed. I have kind of a technical problem here, though. When you do a definite integral, the variable of integration can't show up in the answer because of the antiderivative business, for instance. So if I were to write t here and dt down at the end, that wouldn't really make any sense. However, we can take advantage of the fact that the variable of integration doesn't show up in the answer by doing this. I'll call the variable of integration u instead of t. At t equal a, s will be 0 because I haven't moved any from the initial point. At a given t value, there'll be an s of t value to go with it, which may be large or small, depending on whether speeds are large or small as I travel along the curve. Since I usually can't even calculate specific arc lengths, usually you won't be able to get this formula in terms of nice elementary functions, although, like before, if the derivative is continuous, then the integral certainly exists. You just might not be able to get it with the antiderivative trick. In one particular setting, it is possible to get this in a reasonable way. I'm going to go back and look at that same helix again. The speed worked out to be square root of 29. When I write r prime here, I'm thinking of r as being a function of t. The u variable takes on values which are values of the t variable, so I don't feel that it's ambiguous to write r prime of u as having magnitude radical 29. That seems like an odd comment, but we'll see why that is in a minute. I'll start integrating at the place where the t value is 0. When I integrate, I get s of t is radical 29 times t. If you tell me a t number, I can put it into this formula and tell you how much arc length you've traveled. Conversely, if I solve this equation for t, I can do this. Tell me how far I've traveled, and I'll tell you the t number that went with it. There's a bit of notation that we're going to have to deal with. In Calculus 1, if someone told you that f of x was 2x plus 3, you're given to understand that the formula describes the rule or procedure into which you put an input, and then the f of x is the output. If someone asked you what f of w was, then you would know the answer to that question. F of w would just be 2 times w plus 3. Returning to the example that we were able to actually work out, the helix, if I know what the t value is, then I know what the s value is as well, and vice versa. What we're really interested in, though, are the vectors involved. Ordinarily, we only draw the end point of the vector in to keep the picture nice, but for emphasis, I'm actually going to draw the entire vector in this time. This is an arrow. It's an arrow that goes with this particular vector-valued function. There's a t value that goes with that vector, and there's also an s value. So, for example, this might be the result of making the value of parameter t equal to 1, but there's an arc length that goes with that as well. I could tell you, start at the initial point and travel radical 29 units of distance along the curve, and then draw the vector from the origin to where you stopped, and I would get the same vector. So a perfectly clear way of writing this would be r at t equal 1 and r at s equals radical 29. The strange notation is I'm going to think of the vector as being a function of where I'm at from the reference point. When I write r of s, I don't mean write down the formula for r of t, but just write down s instead of t. When I write down r as a function of s, I want to get that same vector, but I want it to be expressed in terms of the arc length parameter. That sounds like complete gibberish. Let me elaborate. If this were Calculus 1, and I asked you to write down r evaluated at s, you would write the same formula down, except every place where you see the letter t, you would write s down instead. We are no longer in such an elementary situation. When s is arc length, and I want the same vector, I've got to write r of s equals this formula, except I have to express t in terms of s. The easiest way to think about this is this formula tells me how to get a certain vector value of my function that corresponds to a certain time value. This formula tells me how to get that same vector, except I'm expressing everything in terms of the arc length parameter instead. Generally speaking, just like with calculating arc length itself, it's much too hard to actually get your hands on the arc length parameter, much less solve it for t in terms of the arc length parameter, and then literally writing a formula out like this. It turns out that this parameterization using the arc length is useful from a philosophical and descriptive point of view. It turns out that something is very easy. This is a formula that tells me the vector r in terms of parameter s. Even though s isn't t, the derivative of this, using s as the parameter, is still a vector that points in the tangential direction. Let's calculate that vector. This looks much more complicated than just doing dr/dt, but as we're about to find out, something very interesting happens here. Doing the usual calculation, the first two terms combine to give 25 over 29, while the other term is 4 over 29. Adding it up, that's radical 29 over 29, which is 1. This is a tangent vector in the direction of increasing s value, and its length is always 1. This is the unit tangent vector. Of course, this could just be a coincidence. It could have worked out that this is a special vector valued function, and just by luck, the unit tangent vector is just the derivative, with respect to s, that is. The arc length parameter is defined as the integral from some fixed number a to some t value of the magnitude of r prime evaluated at u integrated with respect to u. If you'll go back and look in the calculus book, I believe this was either the first or second semester. There's a thing called the second fundamental theorem of integral calculus, and what it says is, if I have a function defined in this way, even though the function itself may be hard to evaluate, its derivative is not. ds dt works out to be the magnitude of the derivative of r evaluated at t, and for clarity, in this expression, I mean what we meant before we brought this arc length parameter into the picture. This is the speed. ds dt is the instantaneous speed. If our function is smooth, then the speed is never zero. Because of the chain rule, though, I know that dr dt is equal to dr ds times ds dt. dr dt, which is the usual velocity, the usual tangent vector, before normalizing it, is the vector dr ds times some positive function ds dt. So if there was any doubt, dr dt and ds dt point in the same direction, the tangential direction. As a result, dr ds is the usual derivative of r divided by the magnitude of the usual derivative of r. This is the definition of the unit tangent vector. Using the usual parameter to t, what I have to do to find the unit tangent vector is to find the derivative of r, then find out how long that vector is, and then calculate dr dt divided by its length. If I use the arc length parameter instead of t, there's no need to normalize it. The unit tangent vector is just dr ds. Since the length of t is always 1, t dot t is 1, differentiate that with respect to arc length, and you'll find out that t dot dt ds must be 0. dt ds, just as with dt dt in our previous discussion, is at right angles to the direction of travel. dt ds will point in the direction of a right angle vector. So calculate dt ds, divide by its length, and you'll have the principal unit normal vector. The unit tangent vector, which in our new way of thinking is the derivative of position with respect to arc length, always has length 1. The length of t never changes. If the derivative of the tangent vector with respect to arc length is not 0, that means t is changing, even though we know that the length of t is not changing. That means that the direction of the curve is changing. The derivative of capital T with respect to s is going to give us a quantitative measure of how much the curve is different from a straight line, how curved it is, or its curvature. To get a single number, which tells us something about how curved the path is, we will take this dt ds vector and take its magnitude. We'll make up a special name for this. We'll call this number capital K, not to be confused with the vector of length 1 that points in the positive z direction. This is a number. This is the curvature. I used to joke and tell people that it was because people didn't know how to spell curvature, or that it was the German word for curvature, but I actually looked it up, and it turned out that my second thought was a lot closer to the truth than I believed. The K comes from Krümmung, which is the German word for curvature. In the next and last video for this chapter, we'll find out how to calculate the Krümmung for vector-valued functions without doing anything particularly difficult. We will also relate it to the physics of the situation that we started with. In the meantime, I hope everyone has a good day, and I'll talk to you again soon.